Hello, how are you? Okay, looks like we have just another minute or so. And today we're going to be looking at section 11.2, which is probability and complex experiments. All right, did you have any questions before we get started? Okay, and you're able to see the PowerPoint? Okay, then we'll go ahead and get started. Again, we're looking at section 11.2, which is called probability and complex experiments. Okay, so we're going to start by looking at a thing in your book called the Mathematical Task 11.2a, and that's on page 503. It says if you take the clothing items listed here on a trip, how many different outfits can you put together? And we will assume that everything matches, so we don't need to worry about ending up with a really ugly outfit. All right. So those are what we have. We've got 4 different kinds of pants, 2 different shoes, and 3 different shirts. So I'm going to just start by making a list. And so that I don't have to write out the whole word, I'm going to use the first 3 letters. And I'm always going to write pants first and shoes and then shirts. So I've got the abbreviation here, which stands for jeans, sandals, and floral. So I've listed out the different combinations I was able to come up with that involved jeans. So I've got jeans and sandals and florals, jeans, sandals, stripes, jeans, sandals, solid. And so there were 3 different ways to do it using the jeans and the sandals. And then I did 3 different ways, 3 different outfits that involved the jeans and the ballet flats. And then I was able to come up with 3 combinations that involved the capris and the sandals, and 3 different combinations that involved the capris and the ballet flats. And then I did the 3 combinations with the shorts and the sandals, and the 3 combinations with the shorts and the ballet flats. Then I have 3 combinations with leggings and sandals, and 3 combinations with the leggings and the ballet flats. So I came up with 24 outfits. And I noticed that there were 6 outfits with each type of pants, and there were 4 different kinds of pants. So if you think about that, we could multiply the 6 and the 4 together, and that would give us 24. Other than listing all the combinations, what's a simpler way of counting all the outfits? So that was actually part of the question, was can you do it without listing everything all out? And I did notice that there were 6 outfits with each kind of pant and 4 kinds of pants. So that helps a little bit. And we know there's 4 types of pants. Each type of pant had 6 different outfits. Where's the 6 coming from? Well, there's 2 types of shoes and there's 3 shirts. So if we multiply the 2 and the 3 together, that's giving us the 6. And that's always going to work. So the total number of combinations, it's the number of kinds of pants times the number of kinds of shoes times the number of kinds of shirts. So 4 times 2 times 3 gives me 24. Okay, so that was the mathematical task. And again, I think that was on page 503 of your textbook. Okay, so another thing that we could do for this one is make something called a tree diagram. okay? So there were 4 different kinds of pants, and there were 2 different sandals, okay? The complete diagram is pretty messy, but this is showing us that for each kind of pants, we can match them with the 2 different kinds of shoes. And then if I wanted to keep going, for each, there were 3 different shirts. So I would have 3 branches coming out for each one of these. So I think you can see that that would be really messy. Okay, but this brings us to something called the fundamental counting property. It says if event A can occur in R ways, and for each of those R ways, event B can occur in S ways, then if A happens first and then B happens, this can happen in R times S ways. Okay, so that example actually had 3 events, and the first event could happen in 4 ways. That was the 4 kinds of pants. And then the second event could happen in 2 ways. That was the 2 kinds of shoes. And then the third event, that was the 3 different kinds of shirts. So we multiplied the 4 times the 2 times the 3. Okay, and we're going to see this fundamental counting property showing up a lot. So now we're going to take a look at problem number 1. It says the simplest tree diagrams have 1 stage, okay, when the experiment involves just 1 action. So for example, consider drawing a ball from a box that contains a red, a white, and a blue ball. And we're going to draw the tree diagram. So first we start with a single dot, and then we draw a branch for each outcome. And then at the end of the branch, we label it by listing that outcome. So if we have a red and a white and a blue, okay, so this is just a 1-stage tree diagram. Those are the 3 different things that can happen. We could either draw out a red ball or a white ball or a blue ball. Okay, and so we're going to draw some 1-stage tree diagrams to represent several different experiments. First, we could toss a coin. Well, we're either going to see the heads or we'll see the tails. There's 2 outcomes, so there's only 2 branches for that one. Next, we can draw a marble from a bag containing 1 red, 1 white, 1 black. I'm sorry, 1 red, 1 green, 1 black, and 1 white. So since there's 4 different colors, we have 4 branches. Next, part C, choosing a TV program from channels 2, 6, 9, 12, and 13. So for this one, there's 5 different possibilities, so we're going to draw 5 branches. And then part D, spinning the following spinner, where all central angles are 120 degrees. Well, there's 3 different outcomes. We could either region 1, or region 2, or region 3. Okay. So that was problem number 1. Next, we're going to look at problem number 2. In each part, we're going to draw a 2-stage tree to represent the following experiments, which involve a sequence of 2 experiments. Okay. So we start by drawing the 1-stage tree for the outcomes in the first experiment. And then starting at the end of each branch of the tree in step 1, we again draw a 1-stage tree for the outcomes of the second experiment. So my first experiment is tossing a coin twice. So the first time I toss the coin, I'm either going to get heads or I get tails. So right here, this is the first time I toss the coin. And then if I got heads the first time, I toss it again, and I either get heads or tails. So if I get heads on the first time and heads on the second time, I got heads and then heads. if I get heads the first time and then tails, that means I got heads and then tails. Or I can go down here where I toss tails the first time, and then the second time I either toss heads or tails. So if I follow it this, heads first and then heads, I'm sorry, tails first and then heads, then the outcome is tails and then heads, or tails first and then tails. My outcome is tails and then tails. Okay, so over here is the tree, and then over here, I just list the outcomes next to each other. Part B is drawing a marble from a box containing one yellow and one green marble, and then drawing a marble from a completely different box that contains one yellow, one red, and one blue. So the first time you draw a marble out of the first box, you're either going to draw out the yellow or the green. If you draw out the yellow, you go to the second box and you can either draw a yellow or a red or a blue. If you draw a green the first time and then you go to your second box, you can either draw a yellow, a red, or a blue. So we have 6 different possibilities. We could either get a yellow and then a yellow and then a red, or a yellow and then a blue. Or if we drew out a green the first time, we could either draw a green and then a yellow, a green and then a red, or a green and then a blue. Okay. Part C, having 2 children in a family. Well, either the first child is a boy or the first child is a girl. And if the first child is a boy, the second child is either a boy or a girl. So that gives me 2 outcomes, having a boy and a boy, or a boy first and then a girl. Or if we have first a girl, the second child's either a boy or a girl. So we could have the girl first and then the boy, or a girl followed by a girl. So there's 4 different outcomes for having 2 children. Problem number 3, it says trees can have more than 2 stages. So we're going to draw a tree to represent tossing a coin 3 times. So the first time, we could get a heads or a tails. If we got heads the first time, the second time we could either have heads or tails. And then if we had heads and then heads, the third time we could get heads or tails. Okay, so here the top one corresponds to having heads, heads, and then heads. Next we could have heads, heads, and then tails, which is this outcome. Or we could have heads and then tails, and then heads, or then tails. Okay, so every time we have a branching, we have 2 possibilities. And this is the first coin toss. It's either heads or tails. And then here we have our second possibility. If we got first heads, we could have heads on the second or tails. Or down here, if we had tails first, then we have 2 branchings. We could get heads second or tails second. And then at each one of those, we have 2 outcomes. We could have heads or tails. So we end up with 8 different possible outcomes. Did anybody have any questions so far? Okay. Problem number 4, it says, in some cases, what happens at the first stage of the tree affects what can happen at the next stage. For example, one ball is drawn from the box containing one red, one white, and one blue ball, but not replaced before the second ball is drawn. The first thing to do is to draw the first stage. So this is choosing your first ball. You're either going to choose a red or a white or a blue. But notice, if you draw a red the first time and you don't replace it, you can't draw a red the second time because it's no longer in the box. So if you draw a red the first time, there will only be two possible outcomes. You'll either draw a white or a blue. Likewise, if you draw a white the first time, you won't be able to draw a white the second time because there's no whites left in the box. Or if you draw a blue the first time, you won't be able to draw a blue the second time. Okay, so here's what we're doing. We're drawing a ball from a box that contains one white, one red, one white, and a blue, but not replaced. So if the red ball was selected and not replaced, what possible outcomes can you get on the next draw? You'll either get a white or a blue. So if you draw a red the first time, you could either get a white or a blue the second time. Okay, if the white ball was drawn first, what could you get on the next draw? A red and a blue. Those are the possibilities. So if you draw a white the first time, next time you'll either get a red or a blue. Okay, so far we have 4 different outcomes. We could get a red the first time and then a white. We could get a red the first time and then a blue. We could get a white the first time and then a red, or we could get a white the first time and then a blue. Okay, and then it says to do likewise for the case that the blue one's drawn first. So if we draw out the blue ball, the next time we can either get a red or a white. So we see that there's 6 different possible outcomes. Are there any questions so far? Okay. Oh, how many outcomes are possible? 6, because we've got these 6 different outcomes. Next, it says a die is rolled. If it's greater than or equal to a 3, a coin is tossed. So if we get a 3, next we toss a coin. We'll either get heads or tails. If we get a 4, we toss a coin and we get heads or tails. If we get a 5, we toss our coin and get heads or tails. If we get a 6, we toss and get heads or tails. If it's less than 3, a spinner with equal sections of purple, green, and black is spun. So if we roll and we get a 1, next we spin the spinner and we either get purple or green or black. And if we roll a 2, we spin the spinner and we either get purple or green or black. And we can see that there's 14 outcomes. We've got 3 here and 3 here. That gives me 6, 7, 8, 9, 10, 11, 12, 13, 14. For your vacation, problem number 6, you will travel from your home to New York City and then to London. You may travel to New York City by car, train, bus, or plane. So first you get to New York City, you either go by car or by train or bus or plane. And then from New York to London, you can either take a ship or a plane. So you can take a ship or a plane, a ship or a plane, a ship or a plane, a ship or a plane. So CS means you took a car to New York and then a ship to London. CP means you took a car to New York and a plane to London. Okay, down here, PP means you took a plane to New York and then a plane to London. How many routes are possible? We just need to count them up. 1, 2, 3, 4, 5, 6, 7, 8. You get 8 different routes. Any questions so far? Okay, next it says, apply the fundamental counting principle to find the number of routes. Does your answer agree with part B? So remember the fundamental counting principle, that was what we started with, where we said the number of outfits was the number of pants times the number of shoes times the number of shirts. So we're going to multiply the number of ways to get from home to New York City times the number of ways from New York City to London. So there were 4 different ways to get to New York times 2 ways to get to London. So we do 4 times 2 and we get 8. So it does agree. Now we have 2 different ways. We can either just multiply or draw the tree. Number 7 says Apricot Apparel sells 5 shirts that are in different styles. Okay, so that's one thing, is what the style is. 6 different sizes and 10 different colors. How many different kinds of shirts do they sell? So we're going to multiply the number of styles times the number of sizes times the number of colors. So 5 times 6 times 10 gives me 300 different kinds of shirts. Number 8 says, draw a probability tree diagram for drawing a ball from the following containers. An example for the first container is provided. So here, the only difference is now that we're going to put probabilities on our branches. So there's 3 different colors of balls. There's red and white and blue, and there's 1 of each color. So the probability that we draw out a red is a third. The probability that we draw out a white is a third. And the probability that we draw out a blue is a third. So that was the example. And now we're going to do some ourselves. So here I see that we've got the 2 balls. One's red and one's green. So we have 2 branches, one for red and one for green. And we have a 1/2 chance of drawing a red and a 1/2 chance of drawing a green. Next, we have a container that has 4 different colors, 4 balls, 1 of each color. We've got red, green, blue, and white, and we have a 1/4 chance of drawing each color. For the next one, we have 5 balls with 5 different colors, and we have a 1/5 chance of drawing each color. Make sense so far? Okay, problem number 9. It says another white ball is added to the container that had 1 red, 1 white, and a blue. So now we've got 2 white balls. Since there's 4 balls, we could draw a tree that has 4 branches. So here's the branch for getting red. Here is the white ball on the left. Here's the white ball on the right, and then the blue ball. So there's a 1/4 chance of drawing each individual ball. Okay, so we've labeled each of them with a 4th. We could combine the branches. Okay, so we have a 1/4 chance of getting the red ball. We have 2 white balls out of the 4 balls. So we have a 2/4 chance of getting white. And 2/4 is the same as a 1/2. And there is a little typo. This should actually be blue because there is a blue ball also. So we have a 1/4 chance of getting red, 2/4 chance or 1/2 of getting white, and 1/4 chance of getting blue. Does that make sense? Anybody have any questions? All right, so it says since 2 of the 4 are white, the probability of drawing white is 2/4 or a 1/2, and the branches are labeled. Okay. So next, we're going to look at some ourselves. Draw a probability tree representing drawing 1 ball from each container. So for this container, we have 5 balls, 2 reds, and 3 whites. So the probability of drawing out a red is 2/5, and the probability of drawing out a white is 3/5. It's just the number of outcomes that are red out of the total number of outcomes, and the number of outcomes that are white out of the total number of outcomes. And then the next one, we've got 2 blue out of 6 balls. So the probability of drawing blue is 2/6 or a third. And the probability of drawing green is 4/6 or 2/3 because there's 4 green balls out of the 6 green balls. For number 10, it says the branches of a probability tree diagram may or may not represent equally likely outcomes. The given probability tree diagram represents the outcome for each of the following spinners. And we're going to write the appropriate probabilities along each branches. So all the spinners that we look at will have a region A and a region B and a region C, but they're not always going to be equally likely. All right, so here we have this spinner, and all of the sections are the same size, and there's 3 sections. So each section will be equally likely. So the probability of landing on section A is 1/3, the probability of landing on section B is 1/3, and the probability of landing on section C is also 1/3. For this next one, this time, section A measures 120 degrees, so the probability of landing on section A is 120 out of 360. Remember, there's 360 degrees in the complete circle, so the probability of landing on section A is 1/3. Section B only measures 60 degrees, so its probability is 60 out of 360, and that's 1/6. And then C, the angle here is 180, so the probability of landing on section C is 180 out of 360, or 1/2. And then this next one, section C is still 180, so its probability is still 1/2. Section A is now 90, so its probability is 90 out of 360, or 1/4. And then the same thing for section B. Okay, next we have what's called the multiplicative property of probability. It says, suppose an experiment consists of a sequence of simpler experiments, like you flip a coin and then you spin a spinner, or you roll a die and then you flip a coin. The probability of the final outcome is equal to the product of the probabilities of the simpler experiments that make up the sequence. So we're going to be multiplying probabilities. Okay, so number 11 says this spinner is spun twice. First, we draw the 2-stage outcome tree. So at the first time we spin, we'll either get an A or a B or a C. And then the second time we spin, we'll either get A or B or C. Okay, so we have 3 branches, and then after each one, we have a tree again with 3 branches. So this is the outcome tree. Next, it says to turn the outcome tree into a probability tree diagram by labeling all of the branches with the appropriate probabilities. Okay, so we did the probabilities in problem number 10. We saw the probability of getting A was 1/3, the probability of B was 1/6, and the probability of C was 1/2. And those probabilities stay the same. Okay, ready for the next slide? Okay. Part C says determine the probability of each outcome by using the multiplicative property of probability. Okay, so getting an A followed by an A, we multiply 1/3 times 1/3, and that gives us 1/9. To get an A followed by a B, we multiply 1/3 times 1/6, and that gives us 1/18. To get an A followed by a C, we multiply 1/3 times 1/2, and that gives us 1/6. So these numbers at the end, we get by multiplying. So for example, to get a B followed by a B, we multiply 1/6 followed by 1/6. So 1/6 times 1/6 gives me 1/36. Okay, and we're almost done. It says determine the probability of landing on the same color twice by using the additive property of probability. We haven't seen that yet, and I'll show that to you in just a minute. So getting the same color twice means you land on section A and then A, or B and then B, or C and then C. The additive property says this probability we can get by just adding. So we find the probability of AA plus the probability of BB plus the probability of CC. So the probability of AA, that was a ninth. We get that by doing a third times a third. The probability of BB is a 36, and we get that by doing 1/6 times 1/6. And the probability of CC is a fourth. And we're going to get that by doing 1/2 times 1/2. So we just need to add those fractions together. So I went ahead and I got my common denominator. And I end up with 1436, which reduces down to 7/18. Any questions so far? Okay, so now we're going to get the actual property. It says, suppose that an event E is the union of pairwise mutually exclusive simpler events, E1, E2, etc., out to En, where these are some events from the sample space. The probability of event E is equal to the probability of event E1 plus the probability of event E2. Keep adding and so on until you get to the probability of event En. Right? And these probabilities can be viewed as the probabilities associated with the ends of the branches in a probability tree diagram. And mutually exclusive means that the events are disjoint, that they don't have any outcomes in common. So, for example, if you were rolling a die, you can get a 1, 2, 3, 4, 5, or 6. So you could split that up into getting an even number and getting an odd number. There's no outcomes in common. There aren't any even numbers that are also odd numbers. So if you wanted to figure out the probability of getting an even or an odd, you would do the probability of getting an even number plus the probability of getting an odd number. All right. Any questions so far? We'll take a look at just a couple more examples. Problem number 12. It says a marble is drawn from a bag containing 2 white marbles, 1 red, and 1 blue. Without replacing the first marble, a second marble is drawn. So first we draw the 2-stage outcome tree. So at the first stage, we either draw out a white or a red or a blue. If we draw a white the first time, the next time we could draw out the other white ball or the red one or the blue one. If we draw out the red one the first time, remember we're not putting it back in, so we can't draw a red the second time, but the second time we can either get a white or a blue. And if we draw a blue the first time, the second time we'll either get a white or a red. Okay, so that's the outcome tree. Next, we think about the probability tree diagram. So remember, there's 2 whites, 1 red, and a blue. So the probability of drawing a white the first time is 2 out of 4, or 1/2. The probability of drawing a red the first time is a 4th. The probability of drawing a blue the first time is a 4th. Now, you remember you draw out a marble and you don't put it back in. So the second time there's only 3 marbles. So our probabilities will always be out of 3 the second time since we didn't put the first marble back in. If we drew a white the first time, there's still 1 white out of 3 marbles. So the probability of drawing a white the second time is a third. And one of the three marbles is red, so its probability is a third. And the other marble is blue. So one marble out of three is blue. If we draw out a red the first time, now there's two whites and one blue left. So the probability of drawing a white is 2 out of 3, and the probability of drawing a blue is 1 out of 3. If we draw out the blue the first time, now there's no blue left, but there's 2 white marbles out of 3 marbles, so the probability of drawing a white is 2/3, and there's 1 red marble out of the 3 marbles, so its probability is a third. Then it says to determine the probability of each outcome by using the multiplicative probability. So to figure out the probability of drawing a white and then a white, we multiply 1/2 times 1/3, and that gives us 1/6. The probability of drawing a white and then a red, we multiply 1/2 times 1/3, and that gives us 1/6. The probability of white and then blue is 1/2 times 1/3, and that's 1/6. Okay, and to do red followed by white, we multiply 1/4 times 2/3, and that makes us 6. Is that okay? Any questions? For part D, it says determine the probability of getting a red and a white marble by using the additive property of probability. So we want to find the probability of getting a white and a red, but it didn't say that it needed to be in that order. So we could either get the white first and then the red, or the red first and then the white. Okay, and the additive property tells us we can add the probability of white and then red plus the probability of red and then white. Okay, and the probability of white and then red is a 6, and the probability of red and then white is also a 6. So we're adding 1/6 plus 1/6, and we get 2/6 or a third. Any questions? So I think we have enough time to get started on the next problem. I don't know that we'll be able to finish it, but we can start it. So number 13 says, the row of Pascal's triangle that starts 1, 4 would be useful in finding probabilities for an experiment of tossing 4 coins. Interpret the meaning of each number in the row. Well, I'm going to back up and think about some of the other rows first. So if we flip a coin once, we either get heads or tails. So there's one way to get heads and one way to get tails. So we're using this row, which is called the first row. If we flip a coin twice, the outcomes are, well, we could get heads, 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 tails, tails, heads, or tails, tails. So there's one outcome that has both heads, one outcome that has both heads. There's two that have one head and one tail. So we either get the head first or the tail first. There's 2 outcomes. That would be this number. And there's one outcome that has both tails. So we're looking at the second row when we flip 2 coins. If we flip a coin 3 times, we get these outcomes. So we could get heads, heads, heads. There's one outcome with 3 heads. We could get 3 different outcomes that have 2 heads and a tail. So there's 3 outcomes with 2 heads and a tail. We have 3 outcomes that have 2 tails and 1 head. So that's this number. And then there's one outcome that has all 3 tails. So we were looking at the third row of Pascal's triangle. Okay. So now we're going to be looking at the fourth row of Pascal's triangle. So following our pattern, there should be one way to get all heads, 4 ways to get one tail, 6 ways to get 2 tails, 4 ways to get 3 tails, and 1 way to get 4 tails. And there is indeed one outcome that's all heads. There are 4 outcomes that have 1 tail. We either have the tail last, second to last, second, or first. For 2 tails and 2 heads, there are 6 different outcomes, and I've listed them here. 3 tails, there's 4 different outcomes. The heads is either first, second, third, or fourth.